Viral immunity basics. Today we're going to discuss the adaptive immune system, which helps us fight viral infections. Of course, the innate immune system is also important, so we'll touch on that briefly at the beginning, but then we'll focus on the adaptive immune system, which is what's going to identify viruses and get rid of them. But before we begin, some notes. First, social distancing is the frontline approach to avoiding viral infection. You want to avoid large crowds, wash your hands regularly, don't touch your face, and talk from a distance. If the rest of your plan for viral immunity started less than 4 weeks ago, you have a pretty bad plan. That's not to say things like elderberry and zinc won't be helpful, but I'd look at those things more as having a cup in a boat that's taking in a lot of water. They may help, but a bucket or fixing the hole will work much better. And finally, it helps to discuss the difference between bacteria and viruses. Many people aren't aware, but bacteria are living things and viruses are not. They're actually genetic material that gets injected into a cell. This will help us understand one of the forms of T cells that we'll discuss a little later. Innate immunity. The innate immune system, also known as the nonspecific immune system, is important as the first line of defense. When pathogens enter tissues, the innate immune system helps prevent entry and it initiates removal. It does this via cytokine production and a nonspecific attack. It includes barriers and immune cells. Barriers meaning physical barriers such as mucous membranes and epithelial cells, and immune cells such as basophils, neutrophils, eosinophils, dendritic cells, macrophages, monocytes, natural killer cells, and Langerhans cells. Important organs in the immune system. There are a few organs within the immune system that are critical for its function. This includes red bone marrow, specifically in the femur and the humerus, as well as the thymus gland located above the heart. These are maturation sites for cells of the adaptive immune system. There is the mucosa-associated lymphoid tissue, which acts as one of those first barriers just mentioned in areas such as the respiratory system, the gut, and the urinary tract. There are lymphatic vessels and ducts, which pull pathogens through several different stages of filtration. And there are the lymph nodes and the spleen, which are these sites of filtration. Cells of the adaptive immune response. B cells are the first cells we're going to discuss. They are generated, mature, and released from red bone marrow. And their primary job is to recognize pathogens. Essentially, they're snitches. They don't kill pathogens. They're just raising the flag saying, yo, this guy's not supposed to be here. They hang out in the lymph nodes, the mucosa-associated lymphoid tissue, and the spleen, and it's their proliferation during infection that causes swollen lymph nodes. The way they work is some sort of pathogen enters a tissue into the lymph node. B cells recognize antigens, which essentially are how they recognize the pathogen. It's a pattern on the pathogen. And then they begin to release antibodies that tell T cells, hey, this guy's got to go, get rid of him. T cells. T cells first mature in the red bone marrow just like B cells. However, once they leave the red bone marrow, they travel to the thymus for further instructions. In the thymus gland, they can develop into several different types of T cells. There are cytotoxic T cells, which kill infected cells. Remember, I mentioned that viruses are not live. They are essentially just DNA that gets injected into a cell, and it is these cytotoxic T cells that kills these infected cells. There are T helper cells, which help out in this process, essentially, assisting in the termination of pathogens and infected cells. And there are T regulatory cells, which promote immune tolerance. In other words, they prevent the immune system from getting out of control, and they also prevent autoimmunity. Essentially, T cells are soldiers in the battle against viruses and other pathogens. They're taking instructions from antigen presenting cells, such as the B cells I mentioned earlier, the macrophages and dendritic cells, and most cells can kind of raise the flag and let T cells know that they've been infected by a virus. So we have the B cells, which are giving orders, and we have the T cells who are killing pathogens, infected cells, and so on. So now let's just kind of travel around the body and look at some of these lymphoid tissues, such as the spleen, mucosa-associated lymph tissue, and the tonsils, which are essentially a first line of defense for any pathogens we're going to encounter either through inhalation or our food. The tonsils are situated near oral and nasal passages. We have the pharyngeal tonsil, which is going to be exposed to all the air we breathe. You may notice on this picture that the little dot immediately under the pharyngeal tonsil, that's actually the pharyngotympanic tube. That is the tube that goes into the inner ear and equalizes the pressure. When we get an infection in the pharyngeal tonsils and then your child gets an inner ear infection, this is how it happens. It essentially travels from this area, this pharyngeal tonsil area. The infection can travel up that tube and give you an inner ear infection. Then there are the palatine tonsil and the lingual tonsil. This is going to be exposed to any air we breathe in through our mouth, as well as anything that we kind of take in through our food. And the whole point of these tonsils is to catch pathogens before they can get into the respiratory system or the digestive system. They contain T cells and various antigen presenting cells. And this is kind of a interesting layout because obviously these tissues, these tonsils, are going to be exposed to pathogens regularly. The whole point is to detect these pathogens early to sound the alarms. That way, if they do get into the respiratory system or the digestive tract, we can be ready. Here we have a lymph node on the left and the mucosa-associated lymphoid tissue on the right. Now, the MALT, or mucosa-associated lymphoid tissue, are essentially tonsils in the gut, respiratory system, eyes, and urinary system. So the way lymph nodes work is lymph enters into these nodes coming from tissues, and these nodes function as essentially a filter. There are T cells in there, B cells in there, various antigen presenting cells, and as you're filtering the lymph through this, B cells are recognizing the bad guys, T cells are taking them out. You're essentially filtering the lymph, and then the remaining lymph goes out the efferent lymphatic vessel and towards the heart. All lymph flows away from the tissue and towards these ducts, these lymphatic ducts that dump into the venous system that goes to the heart. In the mucosa-associated lymphoid tissue, we have a slightly different layout, but doing the same thing. These mucosa-associated lymphoid tissues are exposed to the external environment. Your gut, while you think it's inside you, is actually a tube. So anything that's going into the gut is going to go through these top cells that kind of look a little like Bart Simpson. These are epithelial cells, which are a line of defense against pathogens. What this image does not show is the mucus that's on top of this. And so what happens is, as these pathogens are exposed to the germinal center, B cells recognize them, tell the T cells what to take out, and here we have the same system. Essentially, any pathogens that come in are going to get filtered. They're going to enter the efferent lymphatics and then make their way up to whichever lymphatic duct that they drain out of into the veins. Now we're going to discuss the lymphatic vessels and the lymph nodes. As you can see, we have quite a network of lymphatic vessels throughout the body, and there are a lot of lymph nodes as well, upwards of around 600 lymph nodes in the body. What happens is, in one of these tissues, let's say the respiratory system or the gut, you don't want these pathogens just sitting in there, especially if you're exposed to, say, a respiratory virus, a virus that functions in the respiratory system, such as the flu or this new coronavirus. You don't want that pathogen sitting there. If the virus sits there and just continues to replicate, it will destroy your lungs. You want to get it out of there. Ideally, you can cough it out before it gets in there, but if you can't, you need this lymphatic system to help filter, destroy, and pull these pathogens out of these systems. So what we have initially, let's say you're exposed to the flu virus and the virus is sitting in the mucosa-associated lymphoid tissue in the lungs. You want the B cells and the T cells to recognize it and start attacking it, and then pull it through this lymphatic system. It's going to come to another lymph node. So if it has proliferated in any way or some of the virus has not been killed yet, this next lymph node that it encounters will hopefully do that trick. And then it will begin pumped through the lymphatic vessels again to the next lymph node, to the next lymph node, until it is eventually filtered through these antigen presenting cells and T cells in the lymph nodes and then dumped back into the blood via the veins. Factors that impair adaptive immunity. There are a number of different factors that can really put a dent in our ability to fight a viral infection. Now, if you're currently paying attention to the coronavirus pandemic going around, you'll notice that most of these factors that I'm about to mention are the comorbidities that are going to make you more likely to develop a severe reaction or death. They include age, in other words, being older, obesity, type 2 diabetes, fatty liver. And now these all work via essentially the same mechanism. You get what's called a myeloid to lymphoid cell skewage, meaning you're going to have more cells that create inflammation and fewer cells of the lymphoid origin, such as T cells, that can recognize specific viruses and target them for destruction and kill them. And you also have thymic involution, which this actually occurs very rapidly in us. Within the first decade, maybe 15 years of life, our thymus will essentially shrink. This is thymic involution, and the healthy thymus tissue is replaced with fatty tissue. This impairs the thymus's ability to make mature T cells that can then be told what they need to kill and kill it. And it also impairs our ability to make T regulatory cells, which makes us less immune tolerant and can skew us towards autoimmune disease. Now we also have a few more acute factors, certainly ones that are more easy to address than, say, obesity, type 2 diabetes, and fatty liver. Those things take months to change, and of course you can't really change your age. But there are other things we do on the day-to-day that can really have a negative effect on our ability to fight a virus. They include circadian disruption, a high-fat diet, leaky gut, poor sleep, being sedentary, which is actually a big one we're going to come back to, smoking, stress, alcohol, and high viral load. We'll get back to why we're keeping the high viral load in the acute section. Now, all of these factors do kind of work with one another. For example, if you have circadian disruption, you also likely have poor sleep, leaky gut, and alcohol can cause poor sleep. It does cause circadian disruption and leaky gut. Stress can do the same. Obviously, smoking, since it involves respiratory tissues, it will impair certainly your local response in the lungs due to damaging the cells within the lungs, as well as creating an inflammatory response throughout the body. Being sedentary is an interesting one because it's really important and it has nothing to do with your weight. Lymphatic vessels do not have strong smooth muscle that contracts and causes them to pump. Your lymphatic vessels are dependent primarily on muscular contraction to milk the lymphatic vessels and pump the lymph up so that it can get dumped into the veins via the lymphatic ducts. So what happens is the lymph from your legs would simply just sit there until you begin walking and the muscles in your legs contract. They're going to pump the lymph up, and valves within the lymphatic vessels are going to prevent it from dropping back down. Same in your arms. Lymph being pumped out of your arms is going to enter the lymphatic vessels, and contraction of the muscles in your arms are going to pump it back into the circulation. And the pressures that happen in the chest during normal breathing, those also help pump the lymph. But the lymphatic vessels do not have strong muscles like arteries that essentially help pump. So being sedentary is an independent risk factor outside of what it's going to do in terms of your type 2 diabetes and obesity risk. Now, high viral load is here simply because all of these factors are going to have an effect on your current viral load. Most people have been exposed to many different viruses, such as cytomegalovirus or the varicella virus that causes chickenpox and, again, shingles, the herpes simplex viruses that cause cold sores, and the human papillomaviruses. So we're looking like 75% of the population have been exposed to this. Epstein-Barr, another one, close to 80%. So most people have viruses sitting in their body, and this viral immune system just knocks those down. They don't go away. Again, it's not a living tissue. It's essentially DNA being inserted into a cell, and some of these viruses can hide away and remain dormant. For example, when chickenpox goes away after it's run when you're a kid, it can come back when you're older as shingles, and that's simply the virus traveling down a nerve root and erupting at the skin. And the reason that this happens is because your viral immunity is being impaired. So having a high viral load, in other words, having a large number of old viruses kind of replicating in your body will impair your ability to fight new viruses. And again, as you get older, as you're more obese, as you're type 2 diabetic, etc., fatty liver, all of these factors are going to impair your viral immunity, so you will get reactivation of these old viruses and an impaired ability to fight new ones. Preventing viral infection begins with staying away. That includes the social distancing measures we discussed early on in the presentation. I would not focus on things like elderberry, vitamin C, and zinc as primary means of promoting a strong viral immune response. Certainly you need to get adequate vitamin C and zinc, and being infected with a virus may increase your needs for these, but I don't think this is a primary defense for promoting high viral immunity. Elderberry can help. I wouldn't think that it's a major factor. It does prevent viral replication. A lot of these studies are in mice, and mice are completely different from us, or cell culture studies. So it's not to say that you shouldn't take elderberry, vitamin C, or zinc, but I wouldn't expect a huge effect from them. Promote strong viral immunity with your lifestyle. A person with low comorbidities will be fine. They may not even become infected, and if they are, they'll have mild symptoms like maybe a cough and a low-grade fever. However, a person with many comorbidities will not be fine, and we don't want to go around these people if we're sick, and we want to do things to prevent them from having to go out in public during pandemics like the coronavirus one going on currently. Your primary defense outside of social distancing measures should be your lifestyle. Sleep well, get outside, be active, eat well, and don't stress. People who follow a lot of my work, my circadian work, and my gut health work know that I talk a lot about resilience, and this is what I mean when I say all the systems are connected, and the resilience in one system is very, very important for the resilience in the other systems, as well as total resilience through your body. So we want a strong gut, we want a strong respiratory system, strong musculoskeletal system, and these things will promote a strong viral adaptive immune system.